In this lesson, we're going to be reviewing content for test 2. So I'm trying to go pretty much in order of the sections that we covered. So as we go through the review, there's several problems, many about 40 plus problems here. Just know that I'm proceeding through this review, covering content from section 1 in chapter 3 up to section 6 in chapter 3. So these first few examples on this page come from section 3.1. If you need further study and reminders, then you can access those previous notes for that help. All right, the question is, state whether the graph of the parabola opens up or down. What determines if a graph of a parabola opens up or down is the a value. So in this problem, our a value is -3, and in this problem, our a value is 5. In example 1, a is a negative number, so a is less than 0. So when a is negative, we open down. And likewise over here, a is equal to 5, and 5 is a positive number. So a greater than 0 means that the graph of the parabola will open up. So for problem 3 and 4, we're told the graph of a quadratic equation, also a parabola, is given. Select the function's equation from the choices given. Well, the parent function starts at the origin, its vertex does, and what we can see is that vertex has been shifted right 4 and up 2. So the vertex of this parabola is 4, 2. Okay, so if I go right 4, then I know in parentheses, I should have an x minus 4. So I'm looking for the parentheses with the square on it where I have x minus 4. So right 4 means that we can eliminate b and c. So right 4 means not the equations b and c. And then we translate up 2. If you translate up 2, then that means we're going to add 2 at the end of the equation. And choice D has us subtract 2, so we want to add 2. So then it's not D, and your answer is A. And just reminding ourselves about the other equations, if B was my answer choice, then my graph should have gone left 4 and down 2. The translations for C would be left 4, up 2. And the translations for D would have been right 4 and down 2. So for example 4, I see that from the origin, the vertex has been shifted right 2, and it looks like down 4. So this ordered pair is 2, -4. So right 2, down 4. So the equation I'm looking for is going to have a -2 and a -4. So the correct answer choice would have been B. This is right 2 and down 4. All right, for 5 through 8, we're asked to find the coordinates of the vertex for the parabolas that are given by each of these quadratic equations. So as a reminder, 5 and 6 are in what we call standard form. That's because we see a set of parentheses with the quantity square on it. Okay, 7 and 8 don't have that parenthesis with the square, so we call this the general form. All right, so we want to find the coordinates of the vertex. I like standard form because it's very identifiable where the vertex is, so I'll use uppercase V to represent the vertex. The vertex we discard, we don't look at the 4. That only has the effect of telling us if the parabola opens up or down, or if we have a stretch or a shrink. But all we want to look at is the vertex. So we go within the parentheses, take the opposite value, and then we go outside the parentheses and we take that exact value. So the vertex over here would be -3, +2. All right, well, in 7 and 8, the vertex is not identifiable, so what we did is we had to use the formula x equals opposite b over 2 times the a value. This gives us the x coordinate of the vertex, and once we get that number, we take that number and plug it back into the function to get the y value, or the other part of the vertex. I'm going to take opposite b, so b is negative 16, so the opposite of negative 16, all divided by 2 times a, and a is 4. So we have 16 divided by 8, and that's going to give us x equals 2. So we need the other half of that vertex. So we plug 2 back into the original problem. Okay, and once we go to our calculator and we do all that work, I believe the answer is negative 10. So this is function notation for the point 2, negative 10, but usually when they ask for the vertex, they want it in the ordered pair form. All right, and same thing here. We'd have to take the same approach. I'll leave this one for you guys. You can check the key with the worked out solutions to kind of self-assess. Let's look at 9 and 10. We're asked to give the domain and range of the quadratic function whose graph is described. So we have a vertex located at this ordered pair and the parabola opens down. So for me, I like a visual. So I'm just going to go ahead and draw a coordinate plane. Let's locate the ordered pair, negative 2. I have to come down 4, so just estimating about right here. I'm going to put the ordered pair here, and I have to come over here and look. Oh, the parabola opens down. So if this is the vertex, then off that vertex, that ordered pair, I'm going to open down. So now we can use our graph to come up with the domain and range. So a quadratic equation that produces a parabola is polynomial, and so the domain is just all real numbers. Now the range, the graph's going to come up from negative infinity, and as high as this graph gets is at a y value of negative 4. So we start with negative infinity, and we go to negative 4, and we can include it, so we put a bracket. Okay. And I'll leave 10. It has the same vertex, but instead it opens up, and then from that graph we can give the domain and range. All right, next objective, determine whether the function is a polynomial function. If it is, identify the degree. Well, if we remind ourselves what it means to be a polynomial function, we need whole number exponents with real coefficients. And then to identify the degree is n, and n is the highest exponent. All right, for problem 11, I first inspect the exponents. Yes, they're all whole numbers. Second thing I test is, do I have real coefficients? 8 and 7 are real numbers, so the answer is yes. The degree is the term with the highest exponent, so the highest exponent is 7, so n equals 7. All right, for 13, is this a polynomial? Well, first thing I do is I'll look for the exponents on the base of x. So 4, 2, and this is an understood exponent of 1. Yes, those are all whole numbers. Then I look at the coefficients, 4, negative pi, and 1/6. Those are all real numbers. They're not imaginary. I don't see any lowercase I to suggest I have imaginary coefficients. So this function is a polynomial. And I think the highest exponent we saw was 4. So the degree is 4. It's a 4th degree polynomial. And 12 is straightforward, so let's look at 14. First thing I do is I look at the exponents. Well, I have an exponent of 4 and 2. This exponent is 1, but the problem is we don't want x in the denominator of a fraction. So we need to rewrite this last term here in a better form to get a better idea of what the exponent really is. So when we want to bring x out of the denominator, we keep the 2 in the numerator. When we bring x up, we bring it up as a multiplication with the 2, but we have to adjust the exponent to a -1. So right now we see that -1 is not a whole number because it's negative. It's an integer, a negative integer. So the answer here is no. There is, and then we don't go further and identify the degree because it's not applicable to what we have. All right, 15 and 16, do the given graphs represent graphs of polynomial functions? So let's make some connections to this language. If we have a polynomial function, then that means that we can draw the graph without lifting our pencil. It's what we call continuous or connected. And then also it has to be smooth, no sharp turns. So I'm looking at 15 and I see that I could draw this graph without lifting my pencil, but the problem is we don't have smoothness going on at x equals 0, so this answer is no. This is not a polynomial. Example 16 is yes, because we satisfy both criteria to be a polynomial function, to be connected and smooth. And one more example here. I had a hard time finding a graph for this. I'm just going to make this graph up. I'm going to say the graph is falling on the left. It comes up here, has an endpoint, and then vertically lining up with this endpoint, I can go anywhere above or below. I'm going to draw an open circle so that I have a function. And I'm going to just say, okay, maybe the graph goes down like this. Would this graph represent a polynomial function? No, because the graph is not connected. I'd have to lift my pencil to draw it. All right, 17 through 20, we're going to use the leading coefficient test to determine the end behavior of the graph of these given polynomial functions. So when it says use the leading coefficient test, sometimes that's abbreviated to LCT. It really means we want to evaluate and look at and analyze what we call the lead term. End behavior means that we want to report our answer as falls and rises on the left and the right. All right, for 17, what we did is we first identified the lead term. To answer this end behavior question, we just want to look at the lead term. So the lead term is going to be either this term or this term. Terms are what we add or subtract, and it's the one with the term with the highest exponent. It has the most impact on this graph, so -2x to the 6th is the lead term. To help us answer this question about falling and rising on the left and the right, I kind of made, I wouldn't say analogy, but a comparison to 4 other graphs. Y equals x to the first with a positive coefficient. Y equals -x to the power of 1 with a negative coefficient. And then y equals x squared with a coefficient of 1. And y equals -x squared. And we looked at these 4 different graphs because they came from our common functions section. And so what we did is we looked at the lead term and we said, oh, this lead term has an even exponent, so I can eliminate the first 2 I wrote down here. So which one of these remaining 2 equations does this lead term model? Well, I have a negative coefficient, so I want to choose y equals -x squared. So I'm going to compare the graph of this function that's given to y equals -x squared. Well, that graph is a parabola that opens down because of the negative a value. So now I can report falls left, falls right. All right, so for 18, let's identify the lead term. Again, and it might not be at the very beginning, it's the term with the highest exponent. They may have scrambled all these terms and put 5x to the 4th at the back end, so be careful. So the lead term is 5x to the 4th. So of these 4 different equations, which one does this lead term mostly model? Well, it has an even exponent with a positive coefficient, so even with the positive coefficient, y equals x squared. Well, y equals x squared is a parabola that opens up. I don't know where to put it. I'm running out of room. So now we can respond to the end behavior question. Rises left and rises right. Odd exponent, negative coefficient. Odd exponent, negative coefficient. So all I have to do is remember, what does this graph look like? It's a linear function, a line that starts up here and finishes down here. So we say rises left, falls right. This term resembles y equals x, odd exponent, positive coefficient. And if we remember, this graph looks something like that. It rises. So falls on the left, rises on the right. In this example, we're going to find the following information and use it to sketch a graph. So we're going to use the leading coefficient test to determine the end behavior. We're going to find the x-intercepts and state the multiplicity for each and whether the graph crosses or touches the x-axis. We'll find the y-intercept. We'll determine if the graph has y-axis symmetry, origin symmetry, or neither. And as a reminder, y-axis symmetry means a graph is what we called even. Origin symmetry means that the graph would be odd. And I'll remind you about that as we get further down into each of these problems. All right, my apologies, this is limited space, so if you wanted to go to paper and do this, then you can kind of spread out your work. It's going to get kind of crowded here. All right, I want to be able to produce a graph of this cubic polynomial function. So let's first determine its end behavior. Well, the lead term is x cubed. That looks like y equals x. So we just did that work. So we know it's going to fall left and rise right. Part B, we're going to find the x-intercepts. That means we set the equation, the y equal to 0. All right, so when I figure out how to solve this for my zeros, because I see 4 terms, I'm thinking factor by grouping. And don't forget with this subtraction, that means the plus 4 becomes a minus 4. Keep the 0. Common factor here is x squared, and when you factor x squared out, we have x minus 4, which is great because we need that same binomial. And I'm at the minus. I'll put a 1 up front. And then we're going to take out our common parenthesis, our common factor, x minus 4, and I'm left with x squared minus 1. I see that this is a difference of 2 squares, so I can factor that binomial again. So I keep the x minus 4, but I'm going to need 2 binomials because I know this difference of squares factors into x minus 1, x plus 1. All right, at this point, we set each factor equal to 0. And let's see if I can kind of jump off of that. So if I set x minus 4, this factor equal to 0, then the solution or the 0 or the root, whatever you want to call it, is x equals 4. Now we want to state the multiplicity. So multiplicity is going to be the exponents that we have on these binomials. So we have a multiplicity of 1 for all 3 of these zeros. So multiplicity 1, odd multiplicity, we have to decide, do we cross or do we touch the x-axis? So with odd multiplicity, we're actually going to cut through the graph, not just hit it and bounce off of it. And same thing with 1 same multiplicity, also crosses. Same thing with x equals -1. So I'm getting the other zeros by setting these factors equal to 0. All right, so now we want to find the y-intercept. That's part C. So the y-intercept's easy. Everywhere you see x, replace it with 0, 0, 0, 0. So that means our y-intercept is 4. The point 0.04 is on the graph. All right, now I'm running out of room. So for part D, determine whether the graph has y-axis symmetry, origin symmetry, or neither. What we did is we replaced all x's with negative x. So I'm looking back at the original equation, and every single x is going to be turned into a negative x. And watch out for your placement, of the exponents. So I'm just going to do minus and then 4 parentheses negative x as opposed to positive x. Minus is next, and then x gets replaced with negative x, and then plus 4. I'm going to have to come up here. All right, then what we did to determine symmetry, it should be a negative x in here, sorry about that. We looked back and cleaned this up, so negative x cubed is going to give us another negative x, and the parentheses are gone. In this next term, we have to square the negative x, which negative x times negative x makes positive x squared, multiplied by 4, so 4x squared with that minus, so minus 4x squared. Here we would distribute the negative into the negative x, so that becomes plus x, and then we have the plus 4. Then what we did is we compared. We have to compare this new function right here. We have to compare to the original problem, f of x. And what we did is we looked for all signs the same. Well, no, I can clearly see that if this is a negative x cubed and that's positive, then that answer is no. So that means there's no y-axis symmetry. What about all signs different? Is every single sign the opposite of what it was in the original problem? Well, the first two terms are opposites, but notice that you have a minus 4x squared and another. Those aren't opposites, so no. All signs same, no. All signs different would mean we'd have an odd function with origin symmetry, but we don't, so we have neither. All right, and in this little small space right here, I'm going to try and draw a graph. Let's see if I can kind of do this here. All right, so now using all this information, let's put it together. I'm going to draw a grid. I see, the first thing I'm going to do is I'm going to put in my x-intercepts, my roots or my zeros, whatever you want to call them. So I need x equals 4 and 1 and -1. So there's -1, +1, 2, 3, and 4. So let's fill in our zeros. And those are the only times I'm going to have an x-intercept. So now I'm going to go to the end behavior, and I'm going to go, oh, it falls left and rises right. So from this furthest left x-intercept, I know I have to fall left. And from the furthest right x-intercept, I have to rise right. So falls left, rises right. Now what I have to do is I have to either touch or cross the x-axis. Well, I never have a touching of the x-axis, so that means that through this x-intercept I got to go above, but I got to come back down, collect this next x-intercept, come back down, and then turn back around so I can get through that third and last x-intercept. Now, how high and how low do these peaks and valleys go? If you want to plug in points, you can. Oh, we have the y-intercept of 4. So I guess we could say that this is at a height of 4. But where does this part of the graph bottom out? You could put in like 2 to the original problem to get where this y-coordinate is. But I think just our objective is just to kind of get a sketch of the graph. So totally acceptable. All right. Now 22, I'm going to leave for you guys. That'll be on the key. This one's kind of a cool little graph because you do have 2 crossings with the x-axis and 1 touching. So I'll leave that for you guys. And like I said, there'll be the worked out solutions on the key that will be available as well. Next, moving on, I think we're in section 3.3 now. Divide using long division. We want to state the quotient Q of X and the remainder R of X. So let's take the divisor and then put the dividend here. We want to look for any missing terms. So the highest exponent is 3. This is a third degree polynomial. And I see that I have 3, 2, 1, and a constant. So I don't have to fill in any 0 placeholders. To do long division, we covered up all terms except for the first term of the divisor and the dividend. And we want to know, what can I multiply 2x by to get 6x cubed? Well, that would have to be 3x squared. So we put 3x squared up top here. This is becoming part of our quotient answer, but then we had to back multiply. So 3x squared times 2x is 6x cubed. 3x squared times -4 is minus 12x squared. Then we had to subtract, which subtracting means take the opposite of all the present signs. So these two terms will cancel. If they don't, we made a mistake. Collecting down, this is positive 10x squared. Bring down the next term. You can bring them all down if you want. Start the process over again. Cover up all but the first term of the divisor and the dividend. What do we multiply 2x by to get 10x squared? That'd have to be 5x. So that's the next term of our quotient. Let's back multiply, get 10x squared. Multiply by -4 and you get minus 20x. Let's subtract, so let's change this to its opposite sign, this to its opposite sign. Now look down vertically, these cancel. Collect, we get 14x. And we'll bring down the constant term. What do we multiply 2x by to get 14x? Well, that'd be 7, just 7. Distribute, that's 14x, happens to be minus 28. Let's subtract, let's add that one, and actually get a remainder of 0. So what we can say is, we can say that 2x minus 4 is actually a factor of this third degree polynomial because we have a remainder of 0. All right, so it says state the quotient and the remainder. So Q of X is this quadratic. And the remainder in terms of X is actually just 0. All right, 24 is divide using synthetic division. So we don't have to do long division, we can do synthetic division. Oftentimes a mistake is made when the students try and figure out what number comes up here that you're going to be using to divide with. Well, I see that my divisor is at x minus 1. That's in factored form. So what zeroes that out is positive 1. So you don't want to put -1 here. It's positive 1. Then I'm looking at the highest degree, which is 5. So the coefficient here, we grab the coefficients, we leave out the x's. But I don't have a 4th degree term, so I'm going to put 0. I do have a 3rd degree term, so I use its coefficient of 2. I don't have a quadratic 2nd degree or a 1st degree, so I need 2 more zeros, and then the constant. We skipped a line, drew a line, we bring down 1 and put it underneath the line, then we multiply and get 1. Oh, I put that in the wrong place. Multiply and get 1, put it underneath the next number, add down, get 1. 1 times 1 is 1. Add, get 3. 3 times 1 is 3. Add, get 3. 3 times 1 is 3. Add, get 3. 3 times 1 is 3. Add, and we get 0. So this is our remainder right here. And again, it looks like x minus 1 is a factor of this 5th degree polynomial. So remember, these are the coefficients of a 5th degree, but when I do division, these numbers are going to be the coefficients of a 4th degree answer. So my quotient in terms of x is 1x to the 4th plus 1x cubed plus 3x squared plus 3x plus 3. And again, we have a remainder of 0. I think that's just a coincidence that I chose those two and they both had remainders of 0. All right, 25, use synthetic division and okay, so I know what I have to do, synthetic division. I might not remember what the remainder theorem is, but when it says to find the indicated function value, they want me to find out what the y is when I plug in -1 to this equation. Now, it'd be as easy as going to your calculator, plugging in -1 for all these x's, and getting an answer. But if your synthetic division work is not present, then we really haven't solved this problem the way they're requesting. So we can find function values easy by plugging in 6 for each of these x's and going to the calculator, but without that work of synthetic division, we chose a different way that's not being requested. So how do we use synthetic division? Well, notice that -1 is not involved in a factor. It's not like with an x. So we actually just take -1 and we use that in synthetic division with these coefficients. So this last number is our remainder, but it's also the function value. So f of -1, if I were to plug -1 in for all these x's, would give me an answer in my calculator of -23. So we found -23 by the requested work, synthetic division, remainder theorem. Even though I didn't quite remember what that was, I could kind of figure it out through the context of the problem. I'm going to leave 26. It's a similar example, just provides more practice for you. All right, 27. I'm going to try and finish this page in this video. All right, use the rational zero theorem. It's like, I don't remember what that is. So what's the context clue to help us? I don't really remember what the rational zero theorem is, but when I see this word list, a list, I'm trying to remember, wait, that's that PQ list of all possible rational zeros. And I'm trying to remember, in this first example, what was my p-value? Well, my p-value is the constant, -10, and my q-value is the coefficient on the lead term, so PQ. And what we did was we created factors of p. So we thought about -10, and the numbers that, the factors of -10, or we can just think +10, 1 goes into 10, 2 goes into 10, and so does the negative. That's why I'm doing plus minus. 5 divides into 10, it's a factor, and so is 10. Same thing with q, but the only factors of 1 are positive and -1. Well, we're not done until we create the fraction p over q. So now we want to take every p and put it over every q. Well, if I put 1 over 1, 2 over 1, 5 over 1, and 10 over 1, I'm really just getting in return the p list. So I'm going to positive, negative, and another shortened way is just to put the plus minus in front of your parentheses that lists the factors. So I guess this must be the rational zero theorem, but all I wanted to take away was a list. When I see that, I think PQ, just make sure we label P and Q correctly. Okay, here's P, it's the same number, -10, but now Q is 5. All right, the factors of 5 would be 1 and 5. Now let's create our P divided by Q list. All right, we're going to take all the P values, divide by 1, so that will generate just the same P list. Now we have to take all 4 of the P factors and put them over Q, the 5 value. So 1 over 5 gives 1/5. 2 over 5 gives 2/5. That wasn't already in our list, so we recorded it again. 5 over 5 gives 1. We already have it. And 10 over 5 gives 2. We don't need to duplicate that. So then we get, this is our entire P over Q list. Actually, I think I'm going to stop there because these problems right here do require some time to develop, and I don't think I have that much time remaining on this video. So we'll pick up with 29 in the next video.